Chapter 4 is on describing data from one variable. Alright. And the first term that we come across is numerical descriptive data, or numerical descriptive statistics. And numerical descriptive statistics are just numerical summaries of data. Like if I was to tell you that the average on the first test in here was a 90.3, or some of the examples the books give things like the proportion of United States residents earning below the poverty level is 11.7% in 2001. So numerical summaries of data. That's numerical descriptive statistics. And then of course we know that statistics are measures that are applied to sample data. Remember that? Statistics goes with sample. Measurements that are applied to sample data. More times than not, we deal with sample data. Very rarely do we, really say that we dealt with the population. It's usually some sample that we're looking at. We also went over a parameter, and parameters are measurements that apply to population data. And so whenever we went over these terms, they were actually referred to in the other sections as like statistics sample or population parameter. But if you just see them alone, you just kind of know that's what they go with. And of course, one easy way is by looking at the first letter: statistics sample, parameter, population. Alright, now inferential statistics. So inferential statistics is concerned with making good guesses or inferences about population parameters using sample statistics. So, I mean, just think about what that would mean to a company maybe marketing something. You know, they want to be able to look at a smaller group or a sample, and then from the data that they gather from that sample, they want to be able to make a guess about how that product or whatever that's being distributed to that sample, how it would be affected maybe over the entire population of where they could sell that product or use that product. So inferential statistics are very, very important. We're first going to go over in our statistical journey of actually calculating a lot of stuff, the arithmetic mean. Most of you have seen this before. So what the arithmetic mean is kind of what you probably won't see it referred to as average, but if you're finding maybe your test average or something like that, then what you're actually calculating is an arithmetic mean. So how do you find an arithmetic mean? Well, you simply add up all the data items, so over how many there are. And this notation, what this means is, this would be the first data item, the second data item, the third data item, so on and so forth until you get to the nth data item. That just means the last data item. So you add all of those up, and then you say that times either 1 over n, the number of data items, or it's probably best to think about this like just divided by n, the number of data items. Anytime you take and you sum up a number of items like this, another way that could be written is the sum of x sub I, where x sub I would be the data items, the first x, the second x, the third x. This symbol right here, this is an uppercase sigma, and in all of mathematics it refers to taking a sum. So anytime you see this symbol right here, you want to think sum. So this is the sum of all of the x values divided by n, the number of data items. And if you think about if you've ever gotten your test average, that's what you do. You take all of your tests, you add them all up, and then you divide by the number of tests you've taken. So that's how you find an arithmetic mean, or just a mean. Now, if we take a mean of a sample, then it's actually called a sample mean. Okay? And there's different notation that's used to tell you if it's a sample, or if it's from a sample, or if the mean is from a population. So if you see this symbol here, x bar, that actually means sample mean. So if we're using a formula that has x bar in it, and that's the way that is, that's x bar. If you see a formula with that, then it's calling for the sample mean. And you find it the exact same way. You add up all of the data items and then you divide by n, the number of data items. The way that your textbook writes this looks a little confusing, they have 1 over n times, and then they write out the sum of all of your x values. But multiplying something by 1 over n is the same as dividing by n. So this is, if you write it this way, it's just kind of making it a little bit more complicated than it needs to be. Everybody in here has taken found a mean before, so it's pretty straightforward. Now, what about a population mean? A lot of the formulas we use will call for a population mean. The symbol we use for a population mean is mu, a lowercase mu. Alright, it kind of looks like a U, except the front side here comes down a little bit. Alright, and so that is, or that stands for population mean. And the only difference, I mean, the formula is the same. It's just instead of a lowercase n for a sample, an uppercase n is used for a population. But you find the values the same way. Really, you just add all the values together and then divide by the number of values or data items. Okay, so I want you to find this sample mean. So here are our sample items. It says it comes from sample data. I'm going to calculate sample mean. So x bar is going to equal the sum of all of the data items. So 4 plus 10 plus 7 plus 15 divided by the number of data items, which is 4. Alright, so that's going to be 14, 21, 31, 36 divided by 4. So that's going to be 9. Alright, so really easy. As easy as you think it would be. No tricks there. Alright. Now this next definition that we're going to go over, we'll come back to a form of this definition that's very important to statistics. It's called a deviation. Alright, we go over what's called a standard deviation. But what is a deviation? Your book says that given some point A and a data point X, then x minus a represents how far x deviates from a. The difference is called a deviation. And what it means by some point A and some data point X, we're just talking about a data value. It's like a number. So there is a very important term called a standard deviation that we'll go over. But just a regular deviation would be the difference between some number A and some other given data point X. You know, if you took one and subtracted from the other, that difference is a deviation. How far one data point is away from another data point. If you've ever taken a test average, then you understand how outliers would affect your test average. And what do I mean by outliers? Numbers that are very far away from other numbers. For example, let's say that you make a 95 on the first test, and 100 on the second test, and a 90 on the third test, and then you made a 50 on the fourth test. Well, that 50, that's an outlier, and that will affect the mean or some other type of statistical measure by a lot. Okay? If the statistical measure is not affected by outliers, then it's said to be resistant. So resistant, if you have a statistical measure, so like a mean or a median or a mode, one of those or two of those actually is not affected by outliers, which we haven't went over a median or a mode yet, but statistical measures not affected by outliers are resistant. So we know that a mean is not resistant because it is affected by an outlier, right? Especially, you know, if you think about like a test average or a homework average, or even, it doesn't matter, other averages. If you have outliers, then they will affect some statistical measures. Alright, another statistical measure that we go over is called the median. Sometimes when you're driving down the road, you may see "stay off the median," right? That's kind of related to what a statistical median is. So what is a median? So the median of a set of observations is the data value in the middle of an ordered, what your book calls an ordered array. The same number of data values is on either side of the median value. Alright, so really the only thing I would see confusing here, it says it's the data value in the middle of an ordered array. That just means a data set, like an ordered data set. If you take a data set and you order it from least to greatest, the number that is in the middle will be the median. Now, what if you have a data set that has an even number of terms, though? Then there's two numbers in the middle. So if your data set has an odd number of terms, then you will have a middle term. But if your data set has an even number of terms, you'll have two middle terms. So if you have two middle terms, you actually want to find the average of those two terms. So add them together and divide by 2, and that would be your median. Alright, so let me show you an example of what I'm talking about. So let's say that we had a data set. Here's our data set: 2, 4, 0, 3, 0, 1, 8, 5, 1, 5, 9. Alright, and we wanted to find the median of this data set. Well, we can't just start going and looking towards the middle because this data set isn't ordered yet. So we need to order this. It can be ordered from least to greatest or greatest to least, but the way that our minds work, it makes the most sense to order it from least to greatest. Our minds work better that way. It just comes natural from counting and things like that, at an early age. So the data set, if we ordered this, would be 0, 0, 1, 1, 2, 3, 4, 5, 5, 8, 9. Alright, so you might, if it's a small data set like this, this is relatively small, even if it's not, you might want to count the number of data items and see, is this odd or is this even? Or does it have an odd or even number of data items? Now, how many data items is that? That's 11. And so that's an odd number of data items. So that means we're going to have a number that's exactly in the middle. Alright, and so 1, 2, 3, 4, 5. The sixth term right here will be exactly in the middle. Notice there are 5 data items on the right of 3, and there are 5 data items on the left of 3. So the data item that's exactly in the middle is 3, so the median is 3. Now, do you think that the median is a resistant measure? Would outliers affect the median? No, they would not. So if you have a group of data items that are relatively close, and then you have one outlier, like instead of a 9, if this would have been 109, that would have definitely been an outlier. That wouldn't have affected the median, would it? Because the median is the data item that's exactly in the middle. Okay. Here's another example. Let's find the median. I'll let you do this one. So 65, 98, 76, 83, 94, 79, 88, 72, 90, 85. So first count how many items there are, sort the data items, and then find the median. Alright, so the first thing that we need to do is we need to order the set of data. So hopefully you have ordered the set of data correctly, because if we get those middle terms wrong, then we're going to get the median wrong. So 65, 72, 76, 79, 83, 85, 88, 90, 94, and 98. And then count the number of data items. So we have 10 data items. So that means we're not going to have an exact number in the middle. We're going to have two numbers in the middle. Alright, so if you take these two numbers here, 83 and 85, you have four numbers to the right of 85 and four numbers to the left of 83. So to find the median, you add the two data items together and divide by 2. You find the average of the two middle terms. Okay, and so it's going to be 168 divided by 2, or 84. So the median is 84. Alright, the next term that your book covers, not that important, but it is a way to deal with outliers so that your mean isn't affected as much by outliers, and it's called a trim mean. Since outliers can greatly affect a mean, a trim mean is kind of exactly what you think it would be. If you trim something, you cut something off. A trim mean is a modification of the arithmetic mean which ignores an equal percentage of the highest and lowest data values in calculating the mean. So imagine you had your set of data, and then say you took off the top 10% and the bottom 10%, and you just used the middle 80% of data items. Then that would get rid of the outliers, more than likely. That's what a trimmed mean is. Alright, so a trimmed mean would be a resistant measure. A regular arithmetic mean would not, but a trimmed mean would. And you might think, well, hey, maybe we could do that with our grades. Well, the only bad thing is, yes, it would take away your very worst grade, but it would take away maybe your very best grade too. So a trimmed mean, you do take away the top and bottom equal percentage of data items. Alright. Another measure of location is the mode. This is another term that you're probably familiar with. The mode of a data set is the most frequently occurring value. Just what it says. The most frequently occurring value. So if you look at a set of data, the number that occurs the most is the mode. Now, what if a number doesn't occur? Like, let's say I had this set of data, and instead of saying the sample mean, we wanted to find the mode. You don't have to write this down. It makes sense though. No number is repeated. So we would say that the set of data has no mode. Okay? Let's say that I had this set of data and I wanted to do the same thing. Find the mode. Now, while you don't have to order the data set to find the mode, sometimes ordering the data set will make it easier for you to figure out the mode. So, let's see, what would I have? 0, 0, 0, 1, 1, 3, 3, 4, 8, 9, 10. All right, so you don't have to sort the data, but by sorting the data you can easily tell that there are 3 zeros. So the mode is 0. If you have 2 numbers that occur the same amount of times, then you have 2 modes. So if a set of data has 2 modes, it's called bimodal. Like bicycle has 2 wheels, bimodal has 2 modes. Now, if we have more than 2 items that are duplicated the same amount of times, then we just say that it's multimodal. All right. Now, for this, these next few terms that I'm going to go over, it's easiest to see by looking at the book. Okay, so let's look here at the relationship between the mean, the median, and then we'll look at maybe the mode. Now, your book says that oftentimes the shape of the data determines how the mean, median, and mode are related. For a bell-shaped distribution, this is called a bell-shaped distribution. It's almost like, you know, if there was one of those little metal things inside this, it would be a bell. You could shake it back and forth and it would make noise. Well, that's called bell shape, a bell-shaped curve, or a bell-shaped distribution. So for a bell-shaped distribution, the mean, median, and mode are identical. I know this doesn't say mode down here, but the mean, median, and mode are identical. if the distribution of the data has a long tail on the right, you can see a long tail, I guess a long tail on the right, then the data is said to be skewed to the right. Okay? Or positively skewed. So while I guess the hump part or the bell part is on the left side, this is skewed to the right. The tail goes to the right. So it's positively skewed. If the distribution has one long tail to the left, like this, then the data is said to be skewed to the left or negatively skewed. Your book says if the data is positively skewed, the median will be smaller than the mean. And if the data is negatively skewed, the mean will be smaller than the median. Alright, this is around page 130 of your ebook. To just be able to visualize the relationship between the mean and the median and the mode, though the mode wasn't listed, is important.